Welcome to the course of Advanced Classical Mechanics. My name is Mikhail Frolov, and we're starting that course of Advanced Classical Mechanics with Lagrange equations. So, Lagrange equations. There are two types of Lagrange equation: Lagrange equation of first kind and Lagrange equation of second kind. Lagrange equation of first kind we will discuss in the first two lectures, and in a further we will discuss Lagrange equation of second kind. In order to introduce Lagrange equation of first kind, so we have to introduce the meaning of constraints. So let me give you three examples of constraints. On the first example, I will discuss motion of bar on the ramp. On the second example, we will discuss motion of three-body system with constraints. In a third example, we will discuss motion of our particle inside of some area. So let's consider first example. So we have a bar, so we have a ramp, we have a gravity force, and instead of vertical motion, which we usually observe when we consider a particle in the gravity force, so we consider just flying down a long off ramp. Why it's happening? So because we have a constraint here, so the y coordinate, Cartesian coordinates, exactly connects with the x coordinate of our bar. So if we know position of x, so we know the position in y. So there is a constraint between y and x, and we can formulate this constraint in that mathematical form. So in general, constraint is some limitation on a motion of our mechanical system. So that is a limitation on position in a space, that is a limitation on velocity, and if we know the constraint for velocity and for a space, then we can obtain some constraint for acceleration. So let's move to the second example. So on the second example, we will discuss our system, which is presented by three particles here. So each particle can be described in terms of three Cartesian coordinates. So first particle having mass m1 and coordinates x1, y1, z1, and all others two have coordinates x2, y2, z2, and so on. So if we consider that system without any constraints, so we cannot talk about the distance between that three particles. So we can consider three-body problem, and that three-body problem cannot be solved analytically and can be solved only numerically. So what's happening if we put some additional condition on the distance between two particles, let's say between particle 1 and particle 3 and particle 2, particle 2 and particle 1. So let's fix that distance. So we fix all the three distances here. So now we have constraint. So if we consider dynamic of that system, so the dynamics of the system will be described by dynamics of the solid. Why? So in general, we have nine parameters or 9 coordinates here, and we have three conditions. So there is only 6 independent variables which describes dynamics of the solid. So let's move to the third example. So the third example presents a particle inside of some area. So here we have some limitation on a distance. Let's say that we have a sphere of radius a, and all position of your particle will be inside of this sphere. So we have some inequality here, and that inequality here is a constraint. Also, we can imagine that there is inside of this sphere there is a daemon, and daemon can control our velocity. So the velocity controller, which we present here, is also constraint. So in order to systemize constraint, so we consider constraints of two kinds. So holonomic constraints or integratable constraints, and non-holonomic constraints, which we call non-integratable constraints. So if we consider holonomic constraints, we can describe in terms of analytical function an equality. And that constraint depends only on the position of particle of our system. There are two types of holonomic constraints. It's a stationary and non-stationary constraints. So in a stationary case, our function does not depend of time. And in a second case, we have explicit dependence on time. So if we consider non-holonomic or non-integratable constraint, in general, it can be described also analytical function, but that analytical function depends on a position and velocity. And also here, so constraint can be described in terms of inequality. So here is just example of constraints which depends on position, velocity, and time, and that constraint is described in terms of equality. So let me give you two examples, and now we should decide in which case we have a holonomic constraint and in which case we have a non-holonomic constraint. So let's consider a particle which moves along the surface of sphere radius a. And second example, we have a particle which moves inside of sphere of radius r. So in which case we have a holonomic constraint. So in first case we have a holonomic constraint. So because we can describe constraint in terms of analytical function which depends on r and equality. In a second case we have a non-holonomic constraint because we can describe in terms of inequality of our systems. So that particle can make a position in any position inside of this sphere. So let me give you further two examples of holonomic constraint. So we have a mathematical pendulum which has a length L, and that L can be changed in time. So that is a holonomic or not holonomic constraint. That is a holonomic constraint, but that is a non-stationary holonomic constraint. So another example here, so we have a rod and we have a square. So square can move along of this rod, which we can describe in terms of analytical function f of x. So can we say that in that case we have a holonomic constraint? Yes, in that case we have a holonomic constraint. On the next lecture we will discuss Lagrange equation of first kind by using constraint which we discussed in this lecture.